In this video, we illustrate how to develop confidence intervals around a mean. Now, let's assume that we are trying to determine how many text messages a young customer would send in a month. The usual approach around this is that we draw a sample from millions of customers. If you are a big company like Bell or Rogers, you have millions of customers. You draw a random sample and then you do a survey and find out the average number of text messages sent by the individuals who responded to your survey, and then you make some inferences about the population from it. That, okay, the survey, we found X number of messages per month. The underlying population would be doing the same. And the question is, can a few hundred customers be sufficient to infer about the entire population of customers? And if that were to be the case, will our average from the sample be the same as average for the population? So you've seen this image in the past, this graphic, the bell curve, and basically what we would like to do is to determine the confidence interval around the sample mean with known population variance. So in this example, we assume that we know the variance or the standard deviation for the average number of text messages sent by young customers in the population, not just in the sample but also in the population. So how do we go about it? The way to do it is we know the following. We did the survey and we know the sample mean, which is called the X bar. We know the population standard deviation sigma, and we know the number of observations in our sample. So if you recall the Z test, which was Z is equal to X bar, which is the sample mean minus the population mean mu divided by the population standard deviation, which further is divided by the square root of the number of observations. So we can rearrange this equation to make it this following equation. And because the sample mean X bar could be greater than or less than the population mean, we replace this minus with a plus minus sign. So far, so good. So to calculate the confidence intervals, we need to determine what is the value for Z, for which we need alpha. Alpha is the area under the normal curve outside the confidence interval area. So this is half of alpha here in one tail and half of alpha here in the other tail. So if our alpha is equal to, say, 5%, which is 0.05, then half of it will be alpha by 2, or 0.025 here and 0.025 here, and 0.95 is the 95% here. Going forward, we can then determine the value for the population mean and the confidence interval around it using the standard normal distribution or the normal distribution. Let's say a telecom company wants to determine the 95% confidence interval for the average number of texts per month sent by a cohort of subscribers who are between the ages of 18 and 24. So we did the survey and we found out that from a survey of 85 respondents, n is equal to 85, we found that the number of texts sent per month is 1300, and the population standard deviation, not just the sample but the population standard deviation, is 160 texts. So we plug this numbers before we plug this number from the standard normal table for 0.95% confidence interval. The value for Z is 1.96. So remember the formula here that I showed in the last slide, which is X plus minus Z times sigma divided by square root of n. So X bar in this case is 1300 minus Z alpha by 2, which is 1.96, times population standard deviation divided by the square root of the number of observations. And then we do the same here with the plus sign, and here's the answer. The answer says that the population mean is somewhere between 1266 texts and 1334 texts. Now here we assume that we knew the sigma, which is the population standard deviation. But in cases where we don't know the sigma or unknown population variance, where we don't know the population variance, so we don't know the standard deviation, what to do then? In those particular cases, we use the t distribution. And for t distribution, not only we need the alpha, but we also need what we call the degrees of freedom, which is n minus 1, basically the number of observations minus 1. Everything else remains the same, except we denote the sample standard deviation as S, which replaces sigma, which was the population standard deviation. So the formula is pretty much same from an empirical point of view. So here's another example. There's a company where workers can work overtime, but instead of being paid for overtime, they can actually take that extra time and take time off for that. So they can add it to their vacation or other time off. So let's say we have a survey done of some 18 employees, and the average extra hours or overtime worked is 13.5 in that sample, and the sample standard deviation is 7.8, so 13.5 hours of extra time on average worked by workers, and the standard deviation is 7.8 hours. The total number of employees we surveyed is 18, and the alpha is 0.1 because now we're working with 90% confidence significance level. So alpha is 0.1, alpha by 2 would be 0.05, and so t value from the t table for t being alpha by 2 being 0.05 and degrees of freedom being 17, that value is 1.74. So x bar is 13.5 minus 1.74, and then times the sample standard deviation divided by the square root of the number of observations. So what we know is that even though the sample average is 13.5 hours, the population mean or the average number of hours were extra worked by the workers within the population vary between 10.3 hours or 10.4 hours and 16.8 hours.